All right. So, and I'm going to pick on Gianna this morning. You're going to start us off with number 7. We've got 2 baseballs are pitched horizontally from the same height, but at different speeds. The faster ball comes across the home plate within the strike zone, but the slower ball is below the batter's knees. So why do the balls pass the batter at different heights? So when you're ready to answer, make sure you're unmuted. Gianna, where are you? Did she get kicked out? No. Yes, Ben?
I have no clue if it's right or not, but I think so. When you throw the ball really fast, it's got that continued force of its speed is carrying it more powerfully in one direction. But if you just toss the ball slower, the outside forces like gravity and the wind and all of that stuff have a stronger effect on it because it doesn't have as much force in and of itself. So it falls more than a faster ball would.
All right. So you are thinking in a kind of right scientific explanation or a physics explanation of this. I don't want you to feel like the ball itself has a force. Okay, we know that the force of the throw is what is carrying these 2 balls. But I want you to think about it in terms of velocity, time, and acceleration. Elizabeth, help him out.
Well, I was going to say if the ball is at a continuous movement, it's still like in a direct path, but so it's just going to stay with a continuous direction. It's not going to accelerate the time is continuous, like it's at its climax, like say pitching,
Okay.
Speed is going to stay the same.
Let's draw a picture because that's what I like to do.
Sorry about that.
Oh, that's okay. I thought maybe you got knocked out of here.
The screen went black and I was like, hello. I didn't know you could hear me.
All right. So here's my sad little baseball. All right, that was supposed to be little threads on there. So we've got one. Oh my gosh, I don't know why it does that. We've got one that has a greater velocity than the other. So it's higher in speed. What force is acting on both of these balls as they're thrown?
Well, gravity is acting on everything, so.
Exactly. So gravity. Gravity is the only acceleration pulling it down. If you throw something, and we know that the distance is fixed, and it's the same. Dylan?
What about wind resistance?
You know better than that. We ignore all that. All right, yeah, in Newtonian physics, a lot of times we ignore that. If we only have gravity working to pull these balls down, which one takes a longer time to get to the batter, Gianna? The fastball or the slow ball?
Is it the faster ball?
Does it take a longer? Yeah, the slower one takes a longer time. So if it's longer in the air, its downward acceleration has more of an effect on it. And so try to relate your answers to velocity, time, and then the acceleration of gravity when you write those up. Ben?
So this is a bit of a meta question, but like
Oh
obviously,
no.
if you're applying physics to sort of art, like architecture and buildings and stuff, obviously there are situations where you have to account for high wind speeds and that kind of stuff.
Oh my gosh, yes, they would use quantum physics.
When you're accounting for environmental factors, what do you do in design?
You would use things like, you know how we use the coefficient of friction? Well, they also have things that relate very similar to that, which are your wind speeds, you know, to affect, so that you know how much of a force can be applied on this building or this bridge without it reaching its maximum. You don't want it to go over its maximum weight or its maximum resistance to that movement. So yeah, it's much more real life. It's applied physics rather than what we're in Newtonian theoretical physics. All right, let's take a look at 8. And Elizabeth, I'm going to have you draw a free body diagram with me. And Paige, you're going to be drawing a motion diagram with me. All
Oh,
right.
drawing, what fun.
I know. So we have an ice cube that slides without friction across a table at a constant velocity. It slides off the table and lands on the floor. So Elizabeth is going to go first. You're going to draw a free body diagram. So remember, those would start out like, oh, look, this is your ice cube on the table. This is your ice cube as it is falling. Okay, so I've drawn your 2 ice cubes. All you need to do is draw the arrows for me.
Okay. Oh my, can I redo this? I'm embarrassed.
Sure.
Alright, and which one do you want me to draw?
Here in just a minute, you're going to be drawing the motion.
Okay.
All right, I'm going to stop you right there, Elizabeth.
If it's sliding, that means the one force is greater.
All right. So let's back up for a second. What is force equal to?
Acceleration divided by
Mass times acceleration, correct?
Mm-hmm.
All right. And we know, oh my gosh, I don't know where that comes from. We know that mass of the ice cube is something because it's an ice cube. But is there acceleration if it's moving at a constant velocity?
No.
All right, so we have no right and left arrows. So go ahead and get rid of your right and your left arrows. So what are the only 2 things acting on the ice cube as it is sliding across the table?
The velocity, there's no.
There's no acceleration because remember, we're drawing forces.
Is it gravity and?
Yes. What's the opposite of gravity?
No gravity.
It does start with an N. It's not weird, it's normal. All right, so draw your arrows of gravity and of normal force. Is it floating in the air or has it crashed through the table?
Because, oh my gosh, I need to.
All right.
They're the same.
Thank you. Yes, they're going to be the same.
They're trying to be the same.
And that is a free body diagram of the ice cube sliding across the table. I'm going to repeat why she doesn't have a right or left arrow. Free body diagrams involve force vectors. There is no acceleration if it's moving at a constant velocity. That means there's no right or left arrow to show anything. All right, now I want you to draw the free body diagram of it falling through the air.
And it's falling to the ground.
Good. Good, good, good. All right. So this is what it would look like for the free body diagram. And now Paige is going to be drawing, let me erase this. Paige is going to be drawing the motion diagram. And motion does not include forces. It just shows us motion.
I'm gonna try my best to at least try to draw. So for like on the table, wouldn't it be like if I can like
Yes.
this?
Yep. And then what about when it's moving through the air? Is there?
And then there's like this. But it's like the arrows are getting like longer this way.
Down or to the right? As it falls, when it very first comes off the table, there's going to be some right arrow and some down arrow.
Yeah.
As it falls, the right arrows will get smaller. And then your down arrows will get bigger until it hits the floor.
Yeah. It's hard
Okay.
to draw with my finger on the iPad.
I know, and I'm drawing with a stylus today, and it keeps on wanting to make weird lines. So oh my gosh, these lines will practically disappear, and then the down arrows will get larger, and then everything stops when it hits the floor. All right. Thank you, girls.
So what exactly should be drawn there? It was hard with all the extra lines.
I know. I don't know why that happens. Just like what Paige did, when it first flies off of the table, you have a line to the right, which is very small because gravity is going to overtake it. And then a line going down, which is a little bit longer than the line to the right, or the arrows, I mean. And then as it falls, if you drew it at 2 more points, the down arrows would get longer and longer because it's moving faster as it drops. All right. Are we ready for a hard one? Yay!
We're really making you work this morning.
You're gonna send this recording out on Classroom, right?
Oh, let me make sure I'm recording it.
It says it is in the corner.
You are.
Oh, good. Oh, yay. Yes, I will. Let me go ahead and shrink down you guys so I can look at the whole thing. All right, Dylan, and who else is here? I only see 4 people. Let's see, Paige, Elizabeth, Dylan,
Yeah.
Ben, Gianna. Oh, Danielle, you're going to help us. All right, Danielle, you still there?
I'm just vibing.
Gotcha. All right. So, Danielle, I want you to read the number 9 to me.
A tennis ball is thrown out a window 28 meters above the ground at an initial velocity of 15 meters per second and 20 degrees below the horizontal. How far does the ball move horizontally before it hits the ground?
All right. So, remember that when we're looking at motion and distance in 2 dimensions, we have to find variables on the y and on the x. So, Danielle, what is the distance on the y? That's the up and down distance.
Well, it says 28 meters above the ground.
You got it. So that's our distance on the y. And I think you said it wanted to know how far it went.
Horizontally before it hits.
Okay. So then we don't know this. We're going to solve for that eventually. And Dylan, how would I write the initial velocity on the x and the initial velocity on the y?
Hang on.
Okay.
Well, on the y, wouldn't it be gravity?
No, we're looking at velocity. So
That'd be
what is,
I don't know.
okay. So he wants to start with y. So I'll start with y with him. So we've got 15 meters per second. That's a 15 times sine of what is our theta? Yeah, so sine of 20 degrees. That's going to be our initial y velocity. Ben, then what would the x be? Instead of sine, what would we use?
Cosine.
All right.
All right. So the 15 times the sine of 20 is 5.13.
That's why I was confused. My block of people was covering up half of these velocities.
Oh, got it. Got it. I shrink my view of you guys when I'm working on this. I gotcha. Meters per second. All right, somebody with a calculator, what is our x initial? 15 times cosine of 20.
14.09.
Okay, we'll do, let's see, it looks like we have 2 sig figs. We'll just do 14. All right, so we're still just doing variables, guys. We haven't even started our problem. So we also know that, not initial, I'm sorry, that the final on the x is going to be the same, correct? Say yes.
Yes.
Thank you. So on the x, your final and your initial velocities remain the same. But we don't know the final on the y. And in order for us to solve for time, that's what we need to solve for first. All right, I'm about to erase this whole board. So if you need it, go ahead and screenshot that.
I've got it copied down.
Okay. All right, so I'm going to clear it. And now we are going to solve first for the final velocity on the y. Since we do not have time yet, we are going to be using, and this is y, vf squared equals vi squared plus 2ad. We're going to use all of the information that we have on the y-axis. Remember, you can't mix your x data and your y data. So we know that our initial y is 5.1 meters per second. And we're going to square this. Plus 2 times 9.8 and then the distance on the y we said was 28 meters. So that's going to give us Fy squared. So what is that answer right now? Somebody, anybody?
This could be really wrong, but I got 574.8.
That's what I got.
I was going to say, that sounds good.
Dr. McCain, why isn't it negative 9.8?
Well, you're going to do 2 times negative 9.8.
Oh, so it's going to be positive.
Yeah, I just left it out because we're going to correct that anyway.
Okay, I got it.
All right. So now do the square root so that we can get the final velocity on the y.
23.974986977.
And we will go with 24. All right. So we need, let's see here.
I was wondering why it was such a big number, but then I forgot we square it.
Right. Yeah, you're good. All right. So now we need to find time. We're going to use this information to find time. I'm just going to put a little square down here. We are finding t. So to find time, we have the final, and that's going to be on the y, equals the initial y plus at. Because I try to always use the easiest way to find our answers. So we can just plug this in, and we have 24 meters per second equals, what do we have, 5.1 meters per second plus 9.8 times t. Now I'm going to rearrange that. The first thing I'm going to do is subtract 5.1 from both sides. I'm going to leave out my units just because of space. Minus 5.1 equals, now it would be 9.8t. How do I get rid of the 9.8, Danielle?
Divide.
Very good. So I'm going to just put t there because we are pretending like I just divided by 9.8. So what is my time? If you do 24 minus 5.1 divided by 9.8.
1.928.
Okay. So with, yeah, with 2 sig figs, we're going to leave it at 1.9 seconds. Now comes the very easiest thing we have to do. Remember, we're I can't talk. I think I just I think I just developed a stutter. I don't know what happened. The easiest thing we need to do now is solve for the distance on the x. All we've been doing up until now is using all of our y data. But the problem actually asks us to find the distance on the x. We had to do all of this to solve for it. So let me clear this. And we have distance on the x is equal to our initial velocity on the x times time. So our initial velocity was 14, actually it should have been 14 instead of 14.1, but it's okay. Meters per second times 1.9 seconds. And Paige, what does that give us as a distance?
For distance, isn't it 27 meters?
Yes, it is. All of that for 27 meters. Whew. And I know it's time for class to be over. However, because I usually only go with you guys for 30 minutes, but I'm not confident. Well, all right, let's look at number 10. If you guys feel confident in number 10, then I'll let you go. We have projectile motion. A softball player tosses a ball into the air with an initial velocity of 11 meters per second. And there's a figure 7. You have to solve for maximum height. And you know that maximum height is going to be your distance on the y before it drops.
This is like what we did in 4 and 5, isn't it?
Very similar. What is our initial velocity on the y is what? Gianna, what are we going to use?
Initial velocity.
All right, but it's on the y-axis. So,
Would it be sine?
yep, sine of what?
Sine of
It's hard to see because it's off to the right, but I guess it'd be kind of 50.
Yes.
I didn't see that.
That's okay. So it's that'll be your initial velocity on the y. When I'm solving for, final velocity on the y, what happens, guys, when a baseball or anything reaches maximum height? What happens to its velocity on the y-axis?
It just turns into gravity, right? Because it just starts falling back down.
All right, for a millisecond.
Oh, it freezes.
Exactly, it is 0. So I want to help you with variables before. So. And the initial distance on the y, well, it's in his hand, so it's 0. And we are solving for final distance on the y.
The initial velocity, 8.43.
Thank you. All right. Do you need any help knowing which formula to use for distance now? Or would somebody like some help?
I would say yes.
All right. Well, when I look at the kinematic equations, what stands out to me is that we do not have which variable that we normally need. And there's no way to solve for it.
Time.
Exactly. So we are going to use the equation in which we do not have time. So we are going to use VF squared. And remember, this is all Y data. VI squared plus 2A. And then the D we are solving for is the distance on the Y. So I'd like for you to use that equation to work through number 10. All right, guys, and those questions, I want you to write up for me, and on Monday, I know we still have a tech day, but on Monday, I just want you to be able to show me a screenshot of your work or a picture of your work, just so that I know that we're doing the best we can. The great news is we are almost to chapter 7. Chapter 7, you really get to take a breath. It's not like this. So bear with me for a little bit longer. All right.
If we get back to school in person, are we going to start doing any kind of like hands-on experiment kind of stuff?
Yes, that's the last thing I got in trouble for. Was for our popper stopper lab. So when we were working with inertia. But yeah, there are labs that I do for all of these chapters. I hate that we can't. Good news is, guys, I got my first round of vaccine yesterday. So
Great.
now, yeah, my arm hurts like can't say those words. It hurts, but
Have you had any symptoms?
Wait till your second shot.
I've heard, no symptoms yet. I've been really cold today. That's the only thing that's weird for me, is that I am freezing cold. But
I'm always.
It's because they put that vaccine in you and they store it at like negative 1,000 degrees. So it's just from the inside out.
It's really weird. My arm hurts and I'm cold, but other than that, I feel fine. So yeah, I go back for my second dose on February the 2nd or 12th. February the 12th, I go back. So yay. All right, guys, it's always nice to see your faces. And I've seen, now that I told my APES kids the really cool present I got for them, we need to figure out something you guys need for physics. So
I'm getting a double whammy this year.
yeah, or you're getting double the presents. It's like having divorced parents.
Quite literally, double the presence of Dr. McKean.
Oh my gosh. All right, for that, I pray for you. You guys have a great day.
Have a great day, Dr. McKean.
You too, Dr.